Welcome to Unfold Data Science. My name is Aman and I am a data scientist. In this particular video, we are going to cover another important piece of the puzzle transformer known as layered normalization. We will also cover one small component with this known as residual connections. So what we are trying to do in this entire playlist, we are trying to understand transformers piece by piece, and then we will go and build LLM powered applications. First of all, we will understand what is the meaning of normalization in machine learning and deep learning to make your concept solid, or if you have forgotten, then it will be a good revision for you. Then we will understand ways to normalize in deep learning. What are the different options in deep learning to normalize? Then we will understand why we use layer norm out of all those options in transformers. I'm going to explain you about residual connections, and while we discuss these concepts, right, in the end, we are going to do everything in Python to get a feel of how things are working together. Okay. So let's go ahead and try to see the transformer architecture first. So that is our starting point basically. We will see this here. And if you pay attention, we have discussed this positional encoding in last video. If you have not watched, please watch that video. Otherwise, it will be difficult for you to digest the complete concept of transformers. So we have discussed what is embedding, how embeddings work, what is positional encoding, how it works. Multi-head attention also we have discussed, and we will discuss add and norm this part today. So if you can see here, the positional encoding and input dimension sum is going into multi-head attention 1, and same thing is going into add and norm as well. So this yellow thing is what we are going to pay focus today, add and norm. First of all, what is normalization in machine learning? Normalization in machine learning is a pretty simple, important, and easy concept. And sometimes in interview, they ask you also these kind of concepts. So to keep it very simple and plain, suppose in your data you have multiple features, feature 1, feature 2, etc. One feature is, let's say, salary feature. And nowadays they give you performance bonus or bonus, right? So I will just say bonus percentage, bonus percent, I will say. So for example, in Indian rupees, somebody's salary is, let's say, 10 lakhs. So I will say like this. Okay. Somebody's salary is, let's say, 15 lakhs. I will say like this. And somebody's salary is, let's say, 20 lakhs. I will say like this. So this is your annual salary. Okay. And there could be a bonus percentage. There could be a bonus percentage. Let's say this person's CTC 15% is bonus percentage, this person's is 12, and this person's is 10. Fine. So in the world of machine learning and data science, it's all mathematical calculations. So what you will do is, if you have to learn some patterns, if you have to use this data for some kind of training, right, you will want to use these numbers. For example, this number, this number, this number, this number, this number, this number. You will want to use these numbers. And from your normal understanding of mathematics, you can think like, if you put these numbers in a mathematical equation, for simplicity, right? Let's take a plus b whole square. Just a simple mathematical equation. And if you put here 10 lakhs plus 15 whole square, right? So something is not right here. Something is not right in the sense that this particular variable or this particular feature is very big in size, and this particular variable or this particular feature is very small in size. So what may happen is few things. What may happen is this variable may override the impact of this variable. That is problem number 1. Problem number 2 is, when you want to optimize some function, loss function, cost function, any kind of optimizers you want to use, right? It will be very difficult for that optimizer because your data is in different shapes and sizes. So it's on different scales. Okay. So it's going to be very difficult for that optimizer to work with that data, right? So in machine learning, right, what we do is we do something known as normalization. So what we will do is, in this data, right, we will create normalized version of this data. So we can have two new columns. So original columns are already there. what we can have is we can have two new columns. One we can call salary. I'm writing N, you can think of normalized. And I'm writing bonus percent B underscore P underscore N. You can think of bonus percent normalized. And what I will do is I will run some mathematical equation and I will start filling these numbers. So what mathematical equations I'm talking about are known as normalization techniques. One such technique is known as mean max normalization. Another technique is known as Z-score method. So two techniques we will see basically. I'll just give you the formula for these two techniques. What you give in mean max scalar is the new value, right? This value we need to compute this value. So how you will compute this new value is basically x minus minimum of x divided by max of x minus mean of x. So this is the formula for mean max scalar. So in the denominator, you take max of x. In this scenario, what will be max of x? Out of 10, 15 and 20, what is maximum? 20. Okay, 20, and you can consider 6 zeros here. Fine. 5 zeros basically. 20 lakhs I'm saying. 20 and 1, 2, 3, 4, 5 zeros. And what is the minimum value here? 10. How many zeros? 1, 2, 3, 4, 5. And what is the x value here? 10, right? Because I'm computing this thing. What is the x value here? 10. 1, 2, 3, 4, 5. And what is the minimum? That is 10. 1, 2, 3, 4, 5. And if you compute this, right, it will become 0. So the normalized value of first row salary column will be 0. Similarly, if you compute normalized value of second row, it will be 0.5. If you compute normalized of third, it will be 1.0. Similarly, if you compute for this column, it will be 1. This will be 0.4 and this will be 0.0. So what we have done is from the original column salary and bonus percent, we have two new columns, salary normalized, bonus percent normalized. And these ranges, right? These ranges are between 0 to 1. How it will help us? It will help us in 5 different ways. I'm going to explain you now. What are those 5 different ways in which normalization helps you? So first thing that normalization does is training stability. So as I was telling you, if you do not normalize, right, what will happen is data will your training will not converge well. Okay, so it can be various kinds of problem. So training stability, faster convergence, I'm knowingly writing here so that you can answer in point wise manner in interview. I told you it will be biased towards large values, right? Avoid bias towards large value. Somebody asks you why do you normalize, you have to tell these things. Helps reduce overfitting. Help reduce overfitting. Why? Because your data will get more opportunity to learn, more flavors of values to learn. And then some activation functions do not like large values. So in that case, it become very, very essential in deep learning, essential for some activation functions like 10H, essential for some activation functions. For example, 10H. So I'll show you the graph of 10H now. In 10H, if you give very large value, there is no use of it. So why do we normalize in machine learning and deep learning? Due to these reasons. What are the different ways to normalize? One way, two ways I'm discussing here. One is min max scalar, another is Z-score method. Now, if somebody asks you, how do you compute Z-score? You simply do x minus mu by sigma. That's it. So what is mu and what is sigma? Mu is basically mean of x and sigma is basically standard deviation. Okay. So this is, you will take x, subtract it from the mean, subtract mean from the x and divide by standard deviation. Whatever comes, that is basically z score of that number. Hence, we call that z score method. So, what you will have after normalization is a new value of salary, new value of bonus percent, and then these things will work nice for you. Training stability, faster convergence, and these reasons. So this is basic of why do you normalize. Now let me try to put it in here so that you can download whatever we discussed now. It will be easier for you to download. I will put it here. Salary is there, bonus percent is there, salary normalized, bonus percent normalized. And which method we have used for normalization? We have used in this one mean max scalar. So what is the formula for mean max scalar? This is the formula for mean max scalar. Okay. What is the formula for Z score normalization? Basically, this is the formula for Z score normalization. So I will write here, compare actual and normalized data. Compare actual and normalized data. Fine. And then this is basically your mean max scaling or normalization. Let's call it normalization to avoid confusion. Mean max normalization. And this, people sometimes normalization and standardization are interchangeably used. Don't worry much about this. Set score, we will keep it normalization only. Normalization. So this is basically basics of normalization and why we need it. Now let's move a step further and try to understand in deep learning why do we need to normalize and what are the ways in which we can normalize and what are the options to normalize. Basically, to understand that, what we are going to do is we are going to take some sentences here. First sentence I will take is basically hi, hi, hello. And second sentence I am going to take is my name is Aman. Fine. So all these will have its own word embedding, right? All these will have its own word embedding. So if you have watched my video on word embedding, you will not have any difficulty in understanding what is embedding basically. So you will know what is embedding. That's not a problem. And when you send data in a deep neural network, right? Suppose this is how you are sending data, right? This is how you are sending data in a deep neural network. What you are going to do is basically you are going to create batches of data. Okay, so you are going to create batches of data. You need to understand how neural network is working internally basically. So you need to create batches of data. Now suppose this is my first entry and this is my second entry. You can simply think of my batch size is 2. There are, let's say, 1 million sentences, but I am sending two sentences together. So my batch size is how much? 2. If my batch size is 2, then these two sentences will go into the model together. When I say these two sentences, right, I'm talking about hi, hello, my name is Aman. So this will have its own word embedding, and similarly all these will have its own word embedding. When I'm trying to send this to a neural network for training, right, I should have a matrix or a tensor that we have been discussing all this while, right? I should have a tensor where I can feed in these values, correct? In this tensor, right, what will be my dimension? So let's fix things here. For example, my batch size is 2. Let's say my dimension of embedding or dimension of model is, for example, 4 in this scenario. Dimension of embedding is 4. So for all these words, we will have 4 numbers. 1, 2, 3, 4. 1, 2, 3, 4. For all these words, we will have 4 number. So finally, what should happen is when you are sending the data, right, that the input sequences all should be of same length. For example, here, if you are saying hi, hello, and here you are saying my name is Aman, what system is going to do is system is going to see what is the largest size in this batch. So size of this is how many tokens here? 2. How many tokens here? 4. So it will just put some placeholder token here and it will call it pad. So what system will do? System will make both these sentences of same length and it will put a placeholder token called this padding. And one key thing here is for padding, we do not have any embeddings. So for padding, it will all be 0. For paddings, it will all be 0. Now, how your matrix will be prepared is hi, hello, hi, hello, padding, padding, okay, and then my, and then name, and then is and Aman. So basically, from here to here is one row, you can say. From here to here is one row of the data, you can say, or one set of input, you can say. And then for all these four numbers will come, and these numbers are nothing but features of your training. So how finally your training data will look like is basically it will have this kind of metric, and wherever I'm ticking right, all these will be one number. How it will look like? Let me paste. I have a diagram here. Let me try to paste and show you. For example, if I have to show you, it will be like this. So hi, hello, pad, my name is Aman. P1, P2, P3, P4, you can think of predictor 1, predictor 2, predictor 3, predictor 4. And whatever you see inside are nothing but embeddings of those data. Fine? Embeddings of that. Now, once you have this right, you have two options here. You have two options of normalizing. One option is normalizing vertically, and another option is normalizing horizontally. So what I'm showing you here is one option is you normalize vertically and another option is you normalize horizontally. So if you normalize vertically, right, you will normalize feature by feature. So see this arrow here. See this arrow here. P1 is one feature. So if you normalize like this, right, then 0 0.1, 0 0.11, 0, 0, 0 0.13, 0 0.14, 0 0.11, 0 0.13. You will normalize like this. And if you normalize horizontally, you will normalize by tokens. For example, you will take hi token, normalize it across features. You will take hello token, normalize it across features. Now pause this video and try to think what is the advantages and disadvantages if we normalize vertically versus if we normalize horizontally. So there are two options, right? So going back to our definition of normalization, we need some numbers to normalize, right? So for example, salary column we normalized with three numbers, 10, 15 and 20. Bonus percent we normalized vertically, 15, 12, 10. My question to you here is, if you normalize by feature like we did here, then what is the problem? And if you normalize horizontally, then how do you think it is making sense? Thinking of transformers architecture. Okay, so one thing I want to write here is basically you need to always remember vertical or feature wise norm or normalization. This kind of normalization is called batch normalization. Okay, what it is called? Batch normalization. And if you do horizontal normalization, right, that is called layer normalization. So horizontal or token wise norm is equal to layer normalization. And one very important thing here, in transformers we use layer normalization. In transformers we use layer normalization. The question is why? Why we can't use feature wise normalization? There are multiple reasons for that. Why we can't use feature wise normalization? The reason number one is, so I will just explain you why we can't use why we can't use batch norm for transformers. Reason number one is, here if you see, right, it is adding some padding here. Okay, and padding, it is adding, system is adding padding because it wants to make the size same, and due to this padding there are zeros getting added. Now imagine in this data here, right, in this data here there are some 3 4 zeros that gets added unnecessarily. What will happen is your entire normalization will get screwed up. Okay, so zero is basically no information, right? Zero is basically no information. So if you are adding zero, there is no meaning of normalizing across, because padding is not a padding is not good for feature wise normalization. Obviously, right, because this is a mathematical computation and you are unnecessarily adding zeros in this, so system does not like that. Okay, so zero padding is one reason why vertical normalization is not recommended in transformers. What is another very important reason why we do token by token normalization? Because transformers process data token by token. Transformer processes data token by token. If you know, I was explaining you how transformer is different from other architectures in last video, right? So basically, transformer will process your data token by token. The previous model, the RN and LSTM, is something that looks front, look in the back, right? Transformer is all parallel processing, right? So it just looks at one token and does what it want to do basically. So the parallelization is very much supported and is in sync when you process token by token input. So this is one key component that you need to understand why it does token normalization basically. The third reason why vertical normalization or feature normalization is not recommended in transformer is many times batch size will be 1. So let me write it here. Batch size of 1 will create problem. What is the meaning of batch size of 1? The batch size of 1 is basically, let's say there is only one input going, basically in inference, right? When you are doing inference in a LLM model, it's normally token by token, one by one. Now suppose one token is going and there is only one number. So for one number, right, there is nothing to normalize. For example, you can think of high word, this first word, and you are doing vertical normalization, and then there is nothing after high. There is only 0.1, one number, that's it. So batch size of 1 will create problem, and hence, that is another reason why we don't go for vertical normalization. And in deep neural network, right, in deep neural network such as transformer, basically a batch normalization, right, batch norm will bring instability. Why it will bring instability is, there's a lot of, if there are a lot of tokens involved and lot of tokens we need to see for feature scaling or one feature normalization, right? It will be problem. Hence, it is recommended to use token by token normalization. Okay. And in terms of speed also, token by token will be uh, basically supported well. So what we do in transformers architecture is basically, if you see here, right, if you see in the diagram of transformer, it will say add and norm, and in norm, right, I will show you, it will say that we are using layer normalization. Encoder, decoder, attention dot product, multi-head, position wide, positional encoding. Let me search. Sublayer of input and normalized, and layer normalization. Okay. So as you can see, we employ a residual connection around each of the two sublayers followed by layer normalization. So it is specifically saying that I'm using layer normalization. So it is not saying it is using batch normalization. So layer normalization is what? Token by token. So it will take one token and normalize. Now, these are the primary reasons why you will go for layer normalization. Why not batch normalization? So one thing is batch normalization good for some scenario? Of course, yes. Batch normalization is good when you have to necessarily take into consideration um, feature by feature basically. So in the image kind of cases, in the CNN, right? Batch normalization is a good option, but not in the sequential world, not in the world of transformers. Fine. And since you have understood how batch normalization or normalization will work, I am just trying to give you formula so that it will be very simple for you. If you can see here, in batch normalization, basically, in batch normalization, what will happen is, as I told you, it will be feature by feature normalization. So here, if you can see, right, it is saying, for example, if you can take P1 as first feature, so x of first minus mu b of first divided by standard deviation square, and this epsilon is basically one small number so that the division should not be by 0. So where mu b and sigma b are mean and variance over the batch of feature k. So suppose this is the first feature. So what it is saying is, go to the first feature, take the mu and sigma of first feature, and this is nothing but x minus mu by sigma. This formula, right? This is x minus mu by sigma. The same thing, x minus mu by sigma. Basically, we are squaring and taking in square root and one small epsilon so that it doesn't become 0. So this is feature by feature. Okay, so what kind of normalization is this? Batch normalization. Batch normalization. And if somebody asks you what is the normalization for layer normalization, so you can give this formula where the new value will be x minus mu features. Mu features means it is basically for, it is coming in horizontally. Okay. So x minus mu of high word, first word if we consider, and sigma square of this first word, and then the epsilon, just to save division by 0 should not happen. And this is the example of layer normalization. Layer norm. This is what kind of norm? Batch norm. And this is vertical. So I will write here vertical or feature wise. Feature wise. And this is layer horizontal or token wise. Token wise. Fine. So by looking at these things, you should always understand how these two normalization techniques are different and why we use layer norm in transformers. Now what we are going to do is we are going to cover one last thing before we go to Python. So one thing that I have not told you is here we are taking the embeddings directly. But usually what gets normalized is not embedding. So I will explain you what gets normalized. So if I go here, right, and if I go to the neural network I had drawn some time back. So in neural network, right, what will happen is these are connected from this through weights, right? For example, this could be W1, this could be W2, this could be W3, right? And at this moment, I want to recommend you one video from Unfold Data Science, and the name of the video is Coding One Neuron from Scratch. Coding one neuron from scratch. You should watch this video to get a solid understanding of how how neural networks are built internally, basically how one neuron works internally. And the reason I'm telling you to learn about this concept is what gets normalized. This is basically one layer, right? This is basically one layer. This is called one layer. When we say layer normalization, right? Here Z is basically Wx plus B. The meaning of Wx is basically W1x1 plus W2x2 plus W3x3 plus B. This is the item which we call Z, and this Z gets normalized, not the original x1, x2, x3, which is basically embeddings. So in other way, what we can think of is basically, in other words, what we can think is to keep it in a form that you can understand. Whenever you are doing a normalization, right, X will be your embedding of input IDs. So X is what? X X is basically these numbers. These numbers, okay? These numbers here are X. These numbers are your inputs. Basically embeddings of input IDs. So these numbers are your X's. And that X will pass through sublayer. Sublayer meaning what? Sublayer meaning it will pass through a attention layer or some other layer. For example, if you go to transformer architecture again, you take the input embedding plus positional encoding, you pass it through multi-head attention, right? So multi-head attention is this sublayer that we are talking about here. Multi-head attention is this sublayer that we are talking about here. So this, what is happening basically, your input is going to the sublayer. This can be a self-attention or feed forward. So you see here it is a self-attention or multi-head attention, whatever. And then this Z gets added to the X. If you see this Z, here you see add plus normal, add and norm. This Z goes back and gets added to original X, and then layer norm applies. So multi-head attention output plus original X. You see this arrow here? This is called original X or residual connection. So this whatever comes out from the multi-head attention plus original X, both these things will come together and pass through normalization layer. That is why add and norm, not only norm, add and norm. Okay. So here we are adding, here we are adding, and here we are normalizing. Here we are adding and here we are normalizing. So what we need to understand is we start with input IDs, we create the embedding. Then we pass that embedding through the sublayer and we get Z. We take that Z and plus it with the original embeddings and then pass through layer norm. This is what is happening here. This is basically output. So as you can see here, it has written residual connection plus layer norm. And this X that you take back, right? This is called residual connections. Why residual connection is needed? Residual connection is needed because we want to store original information as well. As you can see, this is the original information without attention layer. So this is attention layer, original information without attention layer. Both these things will get added and then the normalization will happen. What is the need of basically this adding that? So it will prevent original information and make learning easier. So what will happen? It will, two things will happen from residual connection. Residual connection means this X I'm talking about. Why to keep residual connection basically? Why why keep residual connection? So if somebody asks you, two reason: store, or you can say in one way, keep original info, and second, make make learning faster and easier. Make learning faster and easier. So what are the different reasons for doing this? Basically, it will keep original information and it will make learning faster and easier, because the original information is always retained. Gradients flow directly and it stabilizes the learning. So that is the job of residual connections. Now, if somebody tells you to code this in Python, right? You can take a input embedding, you can generate a multi-head attention output, you can add that with original embedding and then apply the layered norm on that, and that is your output. For example, here I have opened a Python notebook here, and if I have to create some data, right, that can help me to do that. Let me try to do that. So I will just take one token and try to show you. For example, this is my NumPy matplotlib and this is my input token embedding. Just a simple token I have taken. And then what I'm doing is I'm generating my sub layer output. So think like, think like this is output from attention layer. Think like this is output from attention layer. I'm creating it, but you should think like this is an output from attention layer. Fine. Then how residual connections will work is residual connection will be X plus sub layer output. So what will be the, we are doing this yellow part, addition. Okay. So in addition, X should come plus output of attention should come, right? That is what we are doing here. Done. Now what should happen? Layer normalization should apply. For that, I will define a function. So I will take X, as I was telling you, epsilon is a very small number just to avoid division by 0. So here you see, right, everywhere epsilon is there. Very small number just to avoid division by 0. And then I will do X minus mu features by sigma square plus epsilon. So that is what I am doing here. Layer norm is equal to mean is equal to NP mean, standard deviation is equal to this. X minus mean by standard deviation plus epsilon. Same thing basically, either you can take under root or without under root. So I am doing that, and normalized output will be what? We will send that to layered norm residual basically. So residual is a combination of original X plus sub layer output. So let's do this, and we can see all these things basically. So what is our original X input? What is our sub layer output? What is our residual, and what is our layer norm output? Input is this, sub layer output we have created, just created for namesake. After residual, addition of these two, and after layer norm, that formula will apply and you will get the numbers here. So if you compare with transformers architecture, right, these numbers will flow here. Now add and norm will apply. So this is what will flow to the feed forward next layer. And from here it will continue like this. Those numbers will come, it will go to feed forward. Again, add and norm will work. And then it will go to the decoder basically. So we will discuss that later. But to make your concepts clear, right? If you take one token, sub layer output you take, sum it with the same value, that is your residual, pass it through a layer norm, get the layer norm output, and that is what gets feed to the next layer. So this is a simple uh, way of understanding things. The question here is, people may ask you few things from here in your interviews and all, right? They may ask you, why do you use layer normalization? Why not batch normalization? So I gave you a lot of lot of knowledge on that to talk about these 5 4 5 points. Okay, people will ask you, what is the problem if we do batch norm here? You can talk of these points. How the formula works, you can talk of these formula. How the layer norm works on residual, so you can talk like this. Why residual, you can talk like this. One example, you can by hand also calculate. And normalization basics I have already told you. So if you're liking these kind of content, guys, please don't forget to give me a like. That is the motivation for me. See you all in the next video. Wherever you are, stay safe and take care.